So welcome to lecture 31 of MCS 472. This lecture closes off the chapter 10 in our textbook on frequency domain methods. So we use the frequency domain to design plans, and today we're going to go to the topic of control. So we introduced feedback. Now we will see control with feedback. Last time we had feedback on the credit card balance, which could be realized with the first order ordinary differential equation. Today we get to a second order differential equations. The equation that we encountered also with damped harmonic motion. So the control is the first half of this lecture. In the second half we will see two techniques to examine the stability. So there is the root locus method, and then there is the Nyquist analysis. So for both these techniques we will give examples. And I will conclude with two proposals for projects. Okay, so let us consider a control. So with a controller we can have an open loop system. So we have a plant that we want to control. So you can think of temperature control, for example. You set the temperature to a certain desired level, and then the furnace goes on and till the desired temperature is reached. One can see that as an open loop system, but typically there is an automatic temperature control. So we will have then when the temperature drops, so there is still a sensor somewhere that is missing from this picture, but there is feedback. If there is feedback, then we obtain a closed loop control system. So the example that we will consider is the steering control for an automobile. Okay, so that's called a servo mechanism. So we consider a proportional integral controller designed with two parameters. So there are two values for the parameters that we need to fix. So there is the kappa and there is the alpha. So the transfer function for the plant is very simple. It's 1 over s, so that will also make our analysis a little bit easier. So what are our design goals? We want to find values for the parameters that for the unit impulse, so for the step response, so the output to the unit impulse, we have at most a 20% overshoot, and we have a 1 second rise time. So that's the time to reach our goal of 1. So these are two concepts that frequently occur in the control systems literature. We're going to illustrate them here with damped harmonic motion. So that will be the model that will come out of this design. Okay, so we design in the frequency domain. So frequency domain methods is the topic for this chapter. So we have an open loop transfer function. So this is again the idea of two plants that are cascading. So first h, then p. So the transfer function is h times p. When we have feedback, we subtract the output from the input and feed this then back to the system. So we have the transfer function of the open loop system. And instead of the output, the input, the original input, so with the open loop system, we don't have the minus y of s sitting there, but when we do feedback, we have the minus y, the minus of the output, so we subtract the output from the input. Then we rearrange the terms so that at the left we have the output terms, at the right we only have the input, and then the output over the input is the expression then for the transfer function of the closed loop system. Okay, now let's look for our example. So in our model, we have 1 over s as the transfer function for the plant. The controller is a proportional feedback. That's where the kappa comes in. And then there is this differential, this integrator term. So there's one more term that we won't cover here. But there is the proportional integrator and derivative controller, the PID controller, where there is one extra s term there. Okay, so in this transfer function then, we use the formula from the previous slide applied to the specific values for the plant and the controller. So you see now, what do we want? We want to determine the values for kappa and alpha, these two parameters, so that the response of the unit step size has an overshoot of not more than 20% and has a 1 second rise time. Okay, so we have the design in the frequency domain. So to go back to the time domain, we do a partial fraction decomposition. So the first exercise is to justify the last step here in going for the output. So the output to the which is the result of the unit step, the 1 over s. Then verify or justify this partial fraction decomposition. So we saw the formulas in the first half of the course in chapter 3, I guess, when we dealt with Z transforms. Okay, so now let's go to the time domain. So we are, with hindsight here, we're going to get a damped harmonic motion. So we replace the parameters kappa and alpha by more convenient parameters that involve zeta and omega n. So the alpha is omega n to the power 2, and we have this 2 times zeta times omega n as the kappa term. So it looks not simpler at all, but it will greatly simplify the computation of the inverse Laplace transform if we do this. So, and that we use these parameters zeta and omega when we studied damped harmonic motion, when we looked at ordinary differential equations. So that model will occur also here. So in some sense, we already know what we want to obtain. So we have a denominator in our Laplace transform that is a second order, that is of degree 2. So we are going to have a second order differential equation. And most importantly, for this example here, so why do we do this? Well, we want to design parameters. So with the damped harmonic motion there too, going in the notation for the zeta and the omega, we could actually determine the shape of the response. So think about the car suspension mechanism. We want not to overshoot, so we had a design that didn't overshoot, and we could also design how fast the car suspension mechanism returned to its original state. So that is a brief recall of damped harmonic motion. Okay, so we will rewrite the transfer function exploiting the shape of the denominator. So in this model here, I've introduced omega subscript n. I didn't do this with damped harmonic motion. The n was not so relevant here, but here we have an omega d that comes in. So the omega d is important in the rewriting of the denominator. So it looks like we have done another partial fraction decomposition, but we have rewritten essentially the denominator. So we didn't do partial fraction decomposition here. It is a rewriting of the denominator, which will be much more convenient when we take the inverse Laplace transforms. So we have three terms, and we will compute the inverse Laplace transforms of the terms separately. Okay, so here is the code. So in a non-computational course, you would look at the tables. Here we have SymPy, and SymPy exports the inverse Laplace transform. So this contains all the formulas. Important here, is to declare the variables omega and zeta as real. If you do not do this, you get extremely complicated formulas, and also you make the computational time grow larger. So here it's kind of critical that you can add this assumption to the variables so that they are real. So we have two parts. Well, we had the 1 over s, but the 1 over s, the inverse Laplace transform, becomes then the heavy side function, or the 1 for all positive values of t. So we see the heavy side also here occurring. What this mainly means is that the solution only exists for positive values of time. And what do we see? We see that we have a decaying exponential that is common. So the omega will actually be positive, and the zeta will be 2 positive. So for positive values of the two parameters, omega and zeta, we will have a decaying exponential. So that's the first term that we see there. And then we have the oscillations caused by the cosine and the sine function. So in a way, the inverse Laplace transform solves the behavior, the general behavior of this mechanism. So we do have a decay, and we do have the 1 as the equilibrium state. So here this is clear from the formula at the bottom here. So what do we have? At the bottom we have the 1 that is right up front, and then we have the time that is positive and in the long term goes to infinity. So we have this decaying exponential, and you can see that the zeta in particular will determine, and the zeta better be between 0 and 1 because of this denominator there. The zeta will actually determine how fast we go down, how fast the decay is. So then there are the oscillating terms from the cosine and the sine. Okay, so this concludes the first part. So we have the symbolic form of the solution in the time domain. Let's now look at some plots. So we will simulate making plots here to determine the overshoot. So we have two parameters sitting in there. We have a zeta and an omega. Actually, we have two omegas, so that's important here. So we have the omega that is coming from the n, and then the omega that comes from the denominator. So two parameters is one too many. So let's go to what is called normalized time. When we did modeling in the biologically models, we also were able to reduce the parameters to go to dimensionless parameters. We did this essentially also with the pendulum as well. So this is a standard technique in applied mathematics. So we have then an expression in tau. So the tau absorbs also the omega parameter. So what this actually means is that when omega n becomes t, then the omega d is actually replaced. So this becomes then t, this becomes omega n divided by tau, or tau divided by omega n. So I think that here we should now look at the Jupyter notebook, and it's kind of unfortunate that I didn't bring it up. I may actually still do this at some point. Okay, so here we have the plot. So we have the plot for the zeta equals 0.1. So tau runs from 0 to 15, but at this normalized time of 15, the system is still not stabilized, so we still have an overshoot, and the overshoot at time 15 is actually still reaching 20%. So the zeta value is actually way too small to make the decaying term large enough. So the damping should be a lot faster. So we should decay, go to the limit of 1 a lot faster. So then we will make plots for increasing values of zeta. And you see what happens. So the wobbles are getting less and less in size. So we see already when we go to zeta 0.2, we see a noticeable drop, and it drops again at 1 point to close at 0.4. We could keep on doubling. The last value seems to be the best value. We clearly see that we get below the 1.2 mark. So the zeta equals 0.8 will be a very good value. Let's zoom in. So we see that with zeta 0.7, we actually still go a little bit above the 20%. So if we want to be very strict and say that we cannot really tolerate anything that goes above 20%, so if you evaluate, you will get 1.208 or something like that. So if you have no tolerance for that, then go for the zeta equals 0.8. Okay, so that actually solves the design problem. So what do we have? So we pick 0.8 for the safer value for zeta. So the overshoot is less than 20%. We can then set the rise time by going back to the original time. So we have the normalized time tau, and actually we see that for zeta equals 0.8, and you can see this from the picture also, is that we get already very close to 1. Actually, we have 97% already of the 1. Now, again, if you are too strict, if you say, wait, at time 1, I want to get at 1. So this is the rise time. Think about the steering mechanism. It could be that 1 second might be sometimes very critical. So let's really make sure that the rise time is at least 1. So then actually you pick tau equals, that happens, then you have to wait for the normalized time at tau equals 1.1. And then this determines the value for your omega n. So we can then go back to the values for the controller. So the controller had two parameters in there, so the kappa and the alpha. And now we have values for both kappa and for alpha. So that sets the finishes the design of the controller. Okay, that's one example of control. The textbooks has many more, but let's move on to the analysis of the stability. I remind you that when is a system stable? When there is only decay, exponential decay, and that can only happen when all the roots of the denominator of the plant have a negative real part. So there is clearly a geometric notion, a geometric interpretation in this notion of stability. In the previous example, we considered proportional integral control. Here we go back to a simple proportional feedback where we consider kappa. And then the closed loop system, so the kappa is then identified with the h. So in the closed loop system we have q, and the denominator for this example here is then a polynomial of degree 3. So again, this is in the frequency domain, a polynomial that has one parameter kappa. So what we're going to do with the root locus method, we're going to examine the evolution of the roots in function of this parameter kappa. Okay, and now probably I should bring up the Jupyter notebook. So let me see if I can do this in real time. Okay, so there we go. So I hope you see the Jupyter notebook. So here it is. So I'm using SymPy. SymPy has the great benefit that we can work with the symbolic form of the transfer functions just as a rational function. So we have the symbol S, and I was first starting with the Julia package polynomials, but as you divide the two polynomials, it doesn't work anymore, because indeed that operation gets you out of the space of polynomials. Now SymPy has no problem with any general expression, so we defined then also the transfer function of the closed loop system, which has the kappa in there. Kappa is a new symbol. So for selecting the denominator, we have to go to the arguments. So in some sense, this is lecture on symbolic computation again. So we select the denominator um, by multiplying the two arguments. So the first two arguments in this expression are stored by SymPy, or as represented by SymPy, contains the two factors of the denominator. Now inverting then makes it actually not really that simple, but fortunately there is the simplify. So the simplify here at the bottom shows the expression that was also at the bottom of one of the slides. Okay, so we are interested in the roots of this polynomial. Now, SymPy has explicit formulas for the roots of a cubic equation, but that might look extremely messy. So we could actually continue with the generalization of the quadratic formula, so the cubic formula, but let's not go there because we are interested in the representation of the roots. So, and the next slide was dumping a function on this. Now, to understand this function, you have to understand some moves, and it gets a little bit complicated because of the typing system. So if you work with SymPy in Julia, then all the objects are actually symbols. What actually means that they only make sense in the SymPy world. But if you want to do something numerical, and plotting is actually something numerical with them, you have to convert. So with SymPy, you can easily enough select the coefficients in an array. But then I have to be very careful when I substitute. So here I want to replace the kappa by 1. I must explicitly convert to the 64-bit floats that Julia knows so well. Because to find the roots then, with a numerical root finder, I want to start with floating point coefficients. So SymPy has a root finder that when you give it a polynomial with floating point coefficients, you will automatically compute all complex roots. That is very convenient. So I have the coefficient vector. So in some sense it looks very awkward. I started from a polynomial, but then I reconstruct that polynomial again, but I have to do this for the numerical root finder. Okay, so that's part of the input. So we set the input to the root finder, but then you still have the output. So Julia strongly typed, so it's the stuff that you can do with objects is entirely fixed by the typing system. So I have to make sure that what SymPy returns can also be interpreted in the Julia world. And here in particular, I have to explicitly convert the symbols that come back from SymPy, that they are stored in a complex vector known to Julia. And then there's something very awkward, and that's the sorting. So what we are going to examine, we're going to examine the paths of the roots in function of kappa. But the SymPy root finder will return the roots in any order. So in some sense, that's perhaps that's the best way how SymPy computes its roots, but it's very inconvenient for us here. So there is an ad hoc sorting that sorts first on the real parts, and then when there is a tie for two having the same real part, we will then also sort on the imaginary part. So we sort all the roots first on the real part, and if there is a tie, so we have three roots, one real, two complex conjugate. So there will always be, well, here in this example, there will be two roots that will have the same real part. Okay, now I can explain the function locus. So all the moves that I did to prepare the input and to parse and sort the output are summarized in this function. So this course is not a programming course, but in a way with this Jupyter notebook, I want to illustrate how functions are being made. So just by one often gets the wrong impression by looking immediately at the final result. So programmers are very carefully building up statement by statement, essentially. So every statement in this function was tested on the example. And when that every statement worked, then it was assembled into the function. So starting immediately with the function is actually a lot harder. Okay, so then we have the checks. So let's observe also the here on this notebook. I think you don't see it here on the screen, but what you see is that we have the V1 from our original experimentation. And if I scroll further down here, you see that the output of locus for kappa equals 1 is exactly the same. So let me scroll back and forward a little bit so that you can verify. So we have the minus 0.8 and then we have the minus 0.8 again. So that is immediately a check that during the assembling and with potential with some renaming of certain variables that things did not go wrong. Okay, and then we compute the paths of the poles by running this locus method. So the locus function then becomes a function in time here. So I use the t variable for time, but actually it is the value for kappa. From the locus I select the first, the second, and the third. And it's now very inconvenient that I did not run this, but perhaps the plots are all on the slides. Perhaps I can scroll through. So then there are the plotting instructions. So we plot the real and the imaginary parts. So here they are selected. So for all the poles, so the poles are complex numbers. I have to, in the plot, I have to separate the real and the imaginary parts in two separate vectors. So I'm not essentially plotting a function, I'm plotting a curve. So that's important to realize. So we plot functions of, so we have the range, which is the independent variable. So this is the range for kappa from 0 to 2, from 0 to 3, from 0 to 5. And each time we plot the trajectories. Okay, let me pull aside this Jupyter notebook, if that's going to work. I have to resize it. Okay, oops. Okay, so here we go. So this is the Julia function. The final result, and here you see the plots. So we have the three paths. Note the real and the imaginary axis. So the smallest root is very close. So this is a real root. So that was the minus 0.8. So that's, note that what are we actually looking for? We want to determine if this plant is stable, and the first root is good. So the first pole of the, so we are the roots of the denominator. So the first pole of this plant is in the negative left plane. So that's really good. But then you see that for the other two branches, parts 2 and 3, here the real part is actually positive. That's very bad. So we are in an unstable situation. So the feedback, the proportional gain, is not yet large enough. Here you see for kappa equals to 3, the branches get extended, but we still get closer with the real parts to 0, but it's still positive. So for kappa equals 3, it will still be unstable. If we go to kappa equals 5, then you see that the three roots, these three roots here, they are positive. They are all lie in the negative real part. The real parts are all negative. You see that the blue root actually shifts up a little bit. So you can see that with the roots of these polynomials, we have only one parameter here. For the cubic, that's enough. But it might be that you run out of, so this very simple feedback might not be enough. Okay, first exercise is to find the critical threshold for kappa, and we will answer this question later, so I will take that example back up. So that's an easy exercise. The next exercise is actually a little bit, so the code that I presented is correct, is logically correct, but it is terribly inefficient. Of course, with modern computers, computing roots of a cubic goes extremely fast, but you don't really want to do it that way. If you have to do this in a better way. Also, the sorting is really a hack. So for any, you would never want to work like that for other than academic examples. So the next exercise invites you to implement a continuation method. So a continuation method will take a small step size for kappa. So the same step size that we use in the visualization. So if I will not bring up the notebook again, but you see we always, in our range, we have the 0.01. So if we have the roots for one value of kappa, say at 3, we will go to 3.01 with kappa, so set up the problem again. But then we will, instead of recomputing the roots from scratch, we will apply Newton's methods a couple of times, perhaps. If you want full machine precision, you do it three times, but probably one will already be sufficient. And that will make sure that you do not have to do the sorting, because the sorting will actually not work in general. So you can actually already see this on this branch. If you go with kappa equal to 6, then all of a sudden this is no longer the smallest real part. So the coloring is then changing in the red branch. The red branch then all of a sudden becomes blue. And then there are some very funny lines that you then also see. So it's a hack in the sense that it works for the purposes of this example. It's logically correct as well, but it's not a good approach. So try to experiment with what is called a continuation method. So in some sense, this course is also numerical analysis too. Okay, so I have about 10 minutes left to introduce an alternative method. So the alternative method also uses complex plots and is used also for the proportional feedback gain. So with Nyquist's analysis, we make plots of the closed of the part in the closed loops system. So the transfer function of the plant pre-multiplied with the transfer function of the feedback. Then we make a complex plot, And we then can often immediately see if if there is actually a kappa, that if there can exist a kappa that stabilizes the system. Um, Let me illustrate this with an example. So the plot is actually quite easy to make. So we have now a curve again. We have our g function that we evaluate at a range for omega. So this is a complex plot. I have to take the real part and the imaginary part in the curve. And here is the plot where I have s minus 1 for the plant, s minus 2 in the feedback. And what you see is that um, the entire negative real axis lies outside the curve. Um, and there is actually no value for kappa that will stabilize. So there is no gain that will work here. Too bad. Let's see a positive result. So this is the same example as I used with the root locus method. So now we see that the critical value, the critical threshold for kappa is 4. As I'm using the Nyquist analysis, uh, you look for that segment of the negative real axis that is contained in this loop. And you see here we have a tiny segment between negative 1 over 4 and 0, and that is the range for the negative 1 over kappa. So kappa will be larger than 4. So with the Nyquist analysis, we have solved exercise 2. Okay, so why does Nyquist analysis work? Well, we need some complex analysis, so that's actually why it's so nice to illustrate this here. So we have the argument principle from complex analysis. We look in the complex plane, we have a domain, and we have a curve in that domain. We have a function that's very nice, analytic, except for the poles where it's not defined. If the closed curve does not pass to any of the zeros or the poles, then actually by this integral, this contour integral, you will count the difference between the zeros and the poles. And as a consequence, you can count the number of root minus the number of poles. So of course, if you have no denominator, then this works quite well. So you can, so the textbook is a little bit more explicit in its definition, but the argument principle leads to the winding number, and the winding number can be used to find all solutions within a bounded domain or complex roots of any general nonlinear function. So that's also a topic for a numerical analysis project, where we would build a solver based on the winding number. How is this used in control? Well, there is the Nyquist analysis, so named after Nyquist, who came up with the Nyquist contour. So we consider a very specific curve that contains a part of the imaginary axis for some radius and a semicircle. And we actually check that none of the poles actually lie in this region bounded by the Nyquist contour. So in some sense, this is very much related to general root finding, or finding roots of a general function. Okay, so I'm almost done with this lecture. We are actually done with the textbook as well, done with chapter 10. So chapter 10 is very extensive and quite important, and we have not covered everything. One of the topics that we didn't cover was the design of an automobile cruise control system. So this is a little bit more elaborate than the servo mechanism that we considered at the beginning of this lecture. So the project here, so the proposal is to work out that design problem. So first of all, make sure that you understand the solution that is offered in the textbook. So describe the solution in your own words, and also make a computational study of this, very similar like we've done with the root locus method and the Nyquist analysis. So you use one of the two methods. If you can use both, that's fine, but one of the two methods to examine the stability of this solution to design a cruise control system. And as with any project, you should spend, I would say, half the amount of your time on the presentation. So writing the reports is very important here in this course. Okay, so I had the mentioning of the winding number. So I was actually a little bit too fast there. So if you have never seen the notion of a winding number, then that definitely was not sufficient. So this proposal for a project topic is more into numerical analysis, although it's also intended to explore more about software. So if you have taken SAGE, the symbolic computation course that uses SAGE, so one of its components is the computational number theory system Paris GP, which is actually a system that's also quite suitable for doing numerical analysis. And it supports this contour integral. So it would be good if you could implement everything on your own, but that wouldn't be properly a numerical analysis topic, finding the best integrator, numerical integral method for these contour integrals. In this course, it's not a programming course. I would mostly recommend that you look into Paris GP, which is a very nice software system, and do some experiments there. See how it is very useful for the context of finding all complex roots, finding all the complex poles. So try to see if you can actually do the Nyquist analysis there with the Nyquist contour. Okay, so that was it for lecture 31. So there was a lot of ground to cover. I hope this was not too overwhelming. We are closing off chapter 10, introducing control, and also we have the notions of overshoot and rise time. If you would look into the second reference mentioned here, then you also see more definitions with peak time. When does the overshoot reach its peak? Then you can also there are also terms to define when does the when is your system completely stabilized. So, and there are many more control examples. By the way, the damped harmonic motion is also central. So what we examined for the servo mechanism is also quite central in this textbook. So you will also see the root locus method, the Nyquist analysis also explained there. If you want another description, at perhaps a much lower level. So our textbook is much more written at the upper undergraduate level. The textbook of Dorff and Bishop is actually more towards junior engineering students, so it's perhaps better readable. Okay, so I'm running over time. I will close here.